Thank you for coming. I would like to begin today's event with a land acknowledgement. This event is taking place in Toronto, which is situated on traditional land in the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. The territory was the subject of the Bishop One Spoon, One Belt Covenant, an agreement between the Iroquois Confederacy and the Confederacy of the Ojibwe and allied nations to peacefully share and care for the resources around the Great Lakes. Today, this meeting place is still home to many Indigenous people across the Turtle Island, and I am grateful to have the opportunity to work on this land. Acknowledging the traditional territory on which we live and work is a small but important step that reminds us to learn about the Indigenous peoples in these regions, to consider the history and ongoing colonialism in this land, and to reflect on how each of us can contribute to reconciliation. You can visit nativeland.ca and whose.land to learn about the land you are on and who it belongs to. If this is your first time to come to AstroTours, we run tours generally on the first Thursday of most months. After the talk, we will be heading to the lobby and roof of this building, the McLennan Physical Laboratories, and the Astronomy and Astrophysics buildings, which is next to it, for a variety of activities and telescope tours and viewings. There will also be lab tours of the Long Wavelength Lab, which has worked on telescopes such as the South Pole Telescope and CHIME, or the Canadian Hydrogen Intensity Mapping Experiment located in BC. It's a really cool lab, so you should definitely check it out. AstroTours is organized and run by graduate students in the Department of Astronomy and Astrophysics at the University of Toronto, and supported by volunteers who are undergraduate and graduate students in the astronomy and physics departments. We run AstroTours to share our passion, so we really value feedback from our attendees. So after the event, please go to bit.ly/AstroTours to give us the feedback. That's the link right there. So for the upcoming events, before that, we have some merch. If you want to buy AstroTours merch, you can visit that link right there. There's a QR code if you want to check that out. So for the upcoming events, we will have a talk by Simran Nerval. Simran is a PhD candidate.
Oh my goodness. Okay, we have upcoming events first.
Oh. Sorry. So first we have upcoming events. It's this next month, AstroTour. It will be a lecture by Christy about Type 1 supernova. It's going to be on Thursday, December 1st at 8 p.m. If you're interested in that, please come. The location is still being worked out, so check out social media and how you found us, and we'll let you know on how when and where the event will be run. You can also visit the Dunlap Institute Facebook page for upcoming events. Most notably, there will be Cosmos from Your Couch, but also Astronomy on Tap, which will be on November 11th. There will be also a variety of online and in-person events held this month by the Royal Astronomical Society of Canada. So feel free to visit their website to check that out also. So tonight's speaker is Simran Nerval. Simran is a PhD candidate at the Nerval Institute for Astronomy and Astrophysics and the Department of Astronomy and Astrophysics at the University of Toronto. She studies a time period known as inflation, the exponential expansion of the universe within the first fraction of a second after the Big Bang. Simran received her Honours Bachelor of Science in Physics and Astronomy from the University of Toronto, and her Master of Science in Astroparticle Physics and Cosmology from Queen's University. Alongside her research, she spends a lot of time running outreach events with ideas, which stands for Innovation, Diversity, Exploration, and Advancement in STEM. Initiative and AstroTours in order to promote enthusiasm for science in youth and advocate for diversity. In her free time, she is an aspiring baker, baking everything from loaves of bread to decorated cakes. So, here's our speaker.
Hi, I'm gonna take a quick sip of water and switch the. Okay, I just want to confirm, can everybody hear me? Is the mic working? Perfect. Okay, so today I'm going to be telling you all about the growth spurt of the early universe. But before I do that, I should probably, tell you a little bit about what cosmology is, so the field that I study, and what cosmologists actually study. So cosmologists look at the origin, development, and ending of the universe. I, in particular, focus on some of the earliest moments of our universe. So a lot of scientists believe there was some sort of version of a Big Bang that happened, and then within the first fractions of a second after that, it underwent this really, really fast or exponentially accelerating expansion in a time period known as inflation, which I will be mostly focusing on that during this talk. But there's a lot more things that happened in the universe, so I'll give a brief overview of those before I move on. So in the first microsecond, or 0.000001 seconds, our normal matter formed. And then at about 0.01 seconds, we start forming elements, so things like hydrogen and helium. And that continues to happen until the universe is about 3 minutes old. Then we get to a time period known as the cosmic microwave background at about 380,000 years. And we can't actually see before this cosmic microwave background, and I'll explain why shortly, and it's another main topic of the talk. And then nothing really happens until the universe is about 200 million years old, when our first stars and galaxies begin to form. And then, we can fast forward to today and see what our universe looks like at about 13.8 billion years. So yeah, and also how you can read this plot is we have time on the x-axis, and the size of this cone is showing you approximately how large the universe was. So it expanded really, really fast at the beginning, and then it keeps expanding, but at a more steady rate until closer to today, where it's picking up again. But nothing really compares to how fast it expanded during inflation. Okay, so now I'll get into the topic of my talk. And I'm going to start with the takeaway. Don't worry if you don't understand what it means. I'm hoping by the end of the talk, you will be able to understand this statement. And that is, gravitational waves can be used to understand the earliest moments of the universe. But why is this even important? Well, if we can understand how the universe started, we can then try to figure out how and why the universe formed the way that it did. And that's, part of why I'm super interested in these first fractions of a second, to be able to understand why, we see our universe the way that we do. Okay, so I just told you that we can't see before this cosmic microwave background. And I'm going to try to explain to you why. So imagine you were at a party, and it looks something like this. So there's a lot of people, and you wanted to walk to the other side of the room. Well, this is going to be really difficult. You're probably going to hit into a bunch of people, get bounced around, and go in all these different directions. And it's going to take you a really long time to get to the other side of the room. You might not ever even be able to get there. But as the night goes on, people go home, the party dies down a bit, it might look something more like this, where now it's going to be really easy to get to the other side of the room. You probably won't hit into a single person on your way there. Well, this is kind of like the photons or light particles in our early universe. At early times, there are so many matter particles, so things like protons, neutrons, and electrons, that these photons or light particles are bouncing off of them in all these different directions. So just like in that really busy party, they aren't able to leave the room or come towards us. And that happened until the universe got just cold enough that neutral hydrogen and helium began to form. So these matter particles started coming together. And then there was enough room for these photons or light particles to come towards us. And we can take a picture of this time period, and that's known as our cosmic microwave background. And funnily enough, this was actually discovered by accident. So there were two engineers at Bell Laboratories, Arno Penzias and Robert Wilson. They had this gigantic radio telescope that they were using to measure the galaxy and do different satellite communication experiments. But they had this extra signal that they couldn't explain. They ruled out that it couldn't be from the galaxy because they were seeing it from all different directions, and they were trying to figure out if they were seeing it from anywhere on Earth. For a long time, they actually thought that the telescope was filled with pigeon poop because they found some pigeons in there. But after removing the pigeons and cleaning it up, they also were able to rule that out because they still had this extra signal. They were going to just publish this as like a small note in one of their papers, until one of their colleagues told them that they should talk to Jim Peebles, because he was about to publish a paper predicting this cosmic microwave background that we should be able to see from these early moments in the universe. So they talked to him and realized that's actually exactly what they were detecting. And this discovery was so significant that they won the 1978 Nobel Prize in Physics for it. Jim Peebles also won a Nobel Prize in Physics in 2019, not just for this prediction, but for a lot of work he did about the cosmic microwave background, structure formation, cosmic web, dark matter, and a lot of other things. Not only did he do theoretical work on these topics, he kind of revolutionized the way we do cosmology and made it a field where, we can make these predictions, but also tried to figure out how we could connect that to data. And this was all super significant work, so he got the Nobel Prize in Physics for that. Something that's pretty cool as well for anybody that's old enough to have used an analog television is all the static that you see when you go between the channels, about 1% of that is actually the cosmic microwave background. So any of us that have used one of these televisions, we've actually detected it ourselves in our homes. So that's pretty cool. So I should probably show you what this actually looks like now. But to do that, I'd first like you to consider the Earth. So we know the Earth is a sphere, it's three-dimensional. But if we had to look at a globe of the Earth every time we needed directions, that would be really ridiculous. That would be really inconvenient. So we project our three-dimensional Earth down to 2 dimensions. So we make a map of the Earth. So we can look at it on a piece of paper or on a screen. Well, when we're collecting our data of our cosmic microwave background, we're going to be detecting it from all different locations on Earth. So we're going to get a sphere of our data. And just like how we can make a map of the Earth, we can make a map of our cosmic microwave background. So this is actual data from the COBE mission. So this is our universe, what it looked like when it was about 380,000 years old. We measure these light particles, or photons today, to be at a temperature of about negative 270.4 degrees Celsius. Notice how, there's not really much structure here. Everything's the same temperature. It's actually so much the same temperature, it's the same up to 5 decimal places. And this is really weird, and I'm gonna try to motivate to you why. So imagine you were having a potluck, and you invited 2 people over, and both of them brought potato salad. Not only did they both brought potato salad, but then imagine that you invited 1,000 people over, and then all of them brought potato salad. Well, this is really weird and can't possibly be a coincidence, unlike when you just had 2 people that both brought potato salad. And not only did all of them bring potato salad, they all brought the exact same amount. So they all brought 1.000001 kilograms of potato salad. Well, this is just really weird. And it means that they must have all talked to each other or been in contact before your potluck and decided to play this hilarious prank where they all brought the exact same amount of potato salad. Well, this is kind of like the photons or light particles in the early universe. They must have all talked to each other or been in contact early on to all be the same temperature at our cosmic microwave background. But if you remember, the cosmic microwave background was at just about 300,000 years. That means that the farthest that these photons or light particles could have traveled and still been in contact with other ones would be within a radius of about 300,000 light years, where a light year is how far light can travel in 1 year. But that only corresponds to about a degree patch on the sky. So everything larger than these small degree patches shouldn't be the same temperature as each other, but they are. And that's one of the largest motivations that we have for inflation. So here's another version of the history of the universe, but showing a little more exaggerated the different sizes at the different times. So we have that at inflation, the universe expanded so fast. It made it such that it's not just these degree patches that could have talked to each other, it's the entire sky that we measure at the cosmic microwave background. But the universe was really small before inflation. So we have to consider physics at the small scale, or quantum mechanics. Quantum mechanics says that nothing can be perfect and there must be some amount of randomness. So we should be detecting tiny changes, not just this exact same temperature everywhere. And we've actually been able to do that. So here's another version of the cosmic microwave background, this time with data from Planck, where that average temperature is taken away. And we have these really, really small changes in our temperature of the cosmic microwave background, on the order of microcelsius, or 0.000001 degrees Celsius. So these are really small, if you think of just how many zeros there are after that decimal compared to the number of 270. These are really small changes. But they're actually pretty important. These tiny changes in temperature and density is actually what made our galaxies form. And they might seem pretty random, but we can actually get a lot of information from these really small changes. And the way that we do that is, we use computers, and we can get our computer to essentially draw a line on this map and figure out how likely is it that the 2 dots at the end of the line have the same temperature. We can then move that line, figure out how likely it is that these two spots have the same temperature, move it again, figure it out there. Then we can use a different line size, figure out how likely it is that these two spots have the same temperature. Continue to move it around until we've covered the whole sky, go to even more line sizes. And then when we've covered all possible line sizes and covered the entire map, we can put it into something that we call our angular power spectrum. And there's a lot going on here, so don't worry, I'm gonna go through it piece by piece. So our x-axis is showing you our line size, with the largest line sizes on the left going to the smallest line sizes on the right. And then our y-axis is showing us, how likely is it that these 2 points have the same temperature, or their correlations. On the top panels, it's showing you what these fluctuations would look like at these different line sizes. So we have 90 degrees on the far left, so how likely it is that like a point here and here would be the same temperature. In the middle, it's 1 degree, so significantly closer. And then on the far left, it's 0.25 degrees. And then this straight horizontal line is showing you what we should detect if this was a truly random fluctuations and there was no correlations. But the wiggly line is what we actually measure. So that's very different from this straight line. We do have at these really large line sizes, it's pretty close to uniform, but definitely at these like medium and smaller ones, there's a lot of wiggles that are happening. And what we can do once we measure this is we can figure out, okay, what would different models of inflation make these lines look like, and then compare those predictions to our actual data. But to do that, we have to consider, what type of particle is the inflaton, or the particle that causes inflation? Well, it's actually a pretty special particle that can do a lot of cool things. But the closest thing that we have that we've actually detected that we can compare it to would be the Higgs boson. This is a particle that is responsible for giving all other particles their mass. And this was detected in 2012 at CERN, so with the Large Hadron Collider, or the LHC. And this also was such a significant discovery. In 2013, a Nobel Prize was won for it. But one of the important things about this Higgs boson, which is similar to the inflaton, is that it's a scalar field. But what is a scalar field? Well, you can kind of think of it like the temperature in your room. So you could measure, let's say, the average temperature of your room to be about 20 degrees. But you can also measure what the temperature is at all different parts of your room. So we know heat rises, might be a little colder near the bottom, a little hot near the top, but the average still being 20 degrees. You might have an open window, so it's a bit colder there, or a fireplace, it's a bit hotter there. So essentially, with like a temperature, you can measure an average temperature, and then you can measure the tiny changes off of that temperature at different points in your room. Well, that's kind of like what you can think of for a scalar field. So it exists everywhere in space and has an average value, but there's also these tiny changes in the value, just like the temperature in a room. And the way that we like to look at this average temperature, at least for our inflaton, is using something called a potential, which sounds really scary, but you can kind of think of it just like a skateboarder on a ramp. So yeah, the x-axis is showing you how the average inflaton value, or like average temperature in a room, is changing. So we have that this skateboarder is going in this pretty flat part of this potential. So in this purple shaded region is when inflation is actually happening. And we have that during inflation, the skateboarder is moving, pretty slow. This is like a pretty flat part of the potential. But then after inflation, this inflaton is still going to be doing things. And the average temperature is now going to go a lot faster because the skateboarder is essentially in a ramp. So it's going to be changing pretty fast. And those two things are pretty important. So we can use that information to predict what our cosmic microwave background would look like, from this really slow average inflaton value changing to then at the end the really fast changes, which I'll discuss in a bit more detail later. But I told you we can't see before the cosmic microwave background. So how do we actually detect anything about inflation? Well, scientists thought of a pretty cool way, and that's using gravitational waves. So just to remind you, how masses even affect space. Well, here's a grid of space, and we have these 3 balls showing 3 different masses, where here the larger the ball is, the heavier the mass is. And you can see that they're causing the space to become deformed, to make like a well. And the larger the mass is, the more it's deforming space. Well, we can take this abstract concept of masses and actually use that to figure out what it would look like for things like in space, astrophysical things. So LIGO, or the Laser Interferometry Gravitational Wave Observatory, actually detected some pretty cool signals from two black holes merging. And you can see an artist's rendition of what that might look like on the screen here. So you have these two masses and they're orbiting each other. And instead of just causing that well, like you just saw on the last screen, it's causing these ripples to come out, kind of like if you threw a stone into a pond and you had the ripples coming out. So you have these masses orbiting and these like ripples coming out in the fabric of space itself. And this discovery was also so significant that they won the 2017 Nobel Prize in Physics for it. Okay, but we know that we don't live in 2D space, things are 3D. So the way we can look at that in 3D space is using this animation here. Where now, instead of just having like a flat grid of space, we have a cube of space. And we have this mass that's moving around the cube. And you can see the different ways that it's causing this cube to deform as it's moving around. But, everybody here has probably, experienced time. So we know we actually live in 4 dimensions, 3 dimensions of space and 1 dimension of time. And, you can visualize it kind of like this animation on the screen, where we have just like a stationary mass this time in the middle of this grid of space, where there's little clocks at each of the points showing you how time would be behaving. And you can tell that the closer you are to the mass, the more deformed this cube is of space, and the slower the clocks are moving. And the further out you get, the less deformed space is, and the faster the clocks are moving. So yeah, we can try to measure these things, which is pretty cool. But how can inflation actually cause gravitational waves? Well, just like how we had these tiny temperature and density changes that cause things like galaxies to form, we also have these like small changes in our gravitational potential, and that can cause gravitational waves to be formed. But another way that's pretty cool is actually after inflation, when you have like your skateboarder in the ramp part of your potential. And you can get some pretty cool things, which I'll explain in detail here. So just to remind you how like a mass, or you can think of like a pocket of energy, is affecting our space-time. Just to remind you, on the top left there, like we have the skateboarder now going into this ramp, going back and forth. And in this grid of space on the far right, you see these orange things, which are essentially like these pockets of energy density. You're going to think of them as like mass in this space. So you can imagine all of these things are acting like this mass, but there's a bunch of them at all these different locations. So it's causing space and time to change in all these different spots. And as the skateboarder is going around in its ramp, or the average inflaton value, it's going to cause these to change. They're going to get denser and more spherical. And that's going to change the way that it's deforming this box of space-time. And that's going to cause gravitational waves to be emitted. And this will continue to happen until our inflaton has fully decayed or created our particles, like our standard matter that we see, or even something cooler like dark matter. Or it will settle in its minimum, like the skateboarder there, and the gravitational wave signal will stagnate, and it won't continue to increase. Okay, well, how can we detect these gravitational waves? Well, unlike the light particles or photons, how they couldn't get to the other side of the room in this party, you could think of gravitational waves a bit closer to the music in the party. The music doesn't care how many people there are. It can still get through the room. So it's kind of like gravitational waves. It doesn't matter that there are so many light particles and matter particles interacting that they couldn't come towards us at early times. The gravitational waves can still go through them, but it can also affect the people or like the matter and the light particles as they're going through. And that brings us 2 avenues to try to detect them. We can look at, different ways that it's affecting our cosmic microwave background, and we can also look at trying to directly detect these gravitational waves since they're able to go through our party or the early universe. And I'll go through both of these. So I'll first go over the cosmic microwave background. So I'd like you to imagine a slinky, and we're just putting a regular wave through this slinky. It's going to cause the slinky to go up and down, and that's all it's doing. Okay, so if you imagine we just had like one ring of the slinky, the wave's going through it, it's just going to be going up and down. But now let's put a gravitational wave through this one ring of the slinky. So here we have a gravitational wave coming out at us. Instead of it just causing it to go up and down, it's going to cause it to like stretch and squeeze in these opposite directions. So you notice that one side's always stretching while the other one's squeezing. And this can affect our light particles and photons in different ways. So I told you that our light particles have a temperature, but what I haven't told you is that they have electric and magnetic fields as well. So here we have a light particle coming through, and we have these electric and magnetic fields moving with it. Notice that they're at 90 degrees apart or perpendicular from each other. Another way to view it is with this animation, where we have this light particle going and the electric and magnetic fields going with it. I suggest maybe focusing on one of the arrows and seeing how that changes. I'll just grab a sip of water before you do that. Great. So I said that these electric and magnetic fields have to be 90 degrees apart or perpendicular, but I never said they have to be up like this. They can be oriented any way they want. They can be vertical, they can be horizontal, and they could be at any angle in between. And as long as the electric and magnetic fields are 90 degrees apart. And that angle that they're rotated is known as the polarization of our light. So if we were to have a light source that's emitting, vertical light and horizontal light, we could then figure out how much of each polarization we have by having something known as a filter, or here a vertical picket fence, where it has these vertical holes in it, and it's only going to allow this vertically polarized light to come through it. Well, you've used this concept in your day-to-day life if you've ever worn polarized sunglasses. So we have the sun, which is emitting unpolarized light, which means that there's light at all these different polarizations. Then it can scatter off of something like the water, and then your polarized sunglasses are kind of like having two little vertical picket fences, where they're only going to let in the vertically polarized light and block out all the horizontally polarized light. This is actually pretty good for us, because that horizontally polarized light is glare. It's kind of hard on your eyes. But just like how we have these polarized sunglasses that only let in one polarization, we can kind of use that concept in space too. So if we had light from the early universe, it could, scatter off of electrons, like how the light was scattering off of the water, and cause the light to be partially polarized as well. And then we have a detector, which is kind of like having a pair of polarized sunglasses with one vertical and one horizontal picket fence. So you could figure out how much vertical and how much horizontal polarization you had. But, I told you I'd be telling you about gravitational waves, not electrons. Well, just like how electrons can do this, gravitational waves can too. So we have gravitational waves during inflation that can cause the light to become partially polarized. And this means that our cosmic microwave background light is partially polarized. And with our detectors that are like this vertical and horizontal picket fence, we can figure out how much vertical and horizontal polarization we have, and that can help us figure out how much gravitational waves were actually produced during inflation. The way that we look at these polarizations in our cosmic microwave background is using something known as E modes, which in one dimension would be straight up and down or just side to side, and B modes, which are offset by 45 degrees. But we like to look at our cosmic microwave background in two dimensions, right, like a map. So they look a little more complicated, but you can kind of see what they look like in these cartoons on the screen. So on the left-hand side, we have our B mode polarization, or these curled polarization patterns. And on the right-hand side, we have our E mode polarization, or these divergent polarization patterns. And in our cosmic microwave background, they actually look something like this, like in the actual maps. On the top, we have our E mode polarization that has all these divergent patterns. And on the bottom, we have our B mode polarization, so all these curled patterns. And just like how we can look at our temperature fluctuations and make our temperature changes and make our power spectra, we can make power spectra for the polarizations as well to be able to compare them to theories. So just to remind you what our power spectrum looks like, I'm now going to show you first the temperature one, but with actual data plotted on top. So these little dots are actual data from telescopes such as Planck on our temperature power spectrum. We can also put our E mode power spectrum, so how likely it is that the two lengths of the line, so the two dots at the end of the line, would have the same polarization. And you can have our B mode polarization power spectrum. Notice that the B mode spectra has really large error bars, which means that we're pretty uncertain with the measurements that we've taken here. And a lot of current and future experiments are trying to tighten these error bars and get better measurements so we can figure out what happened in the early moments of the universe. Especially because inflation affects this B mode polarization power spectrum the most. And I'm going to try to show you why. So here are just some B mode power spectra that I simulated. So this red dashed line is showing you if there was no gravitational wave production during inflation. Then let's add in some gravitational waves. You can see at these largest line sizes, the power spectrum starting to increase a bit. And if we add in more and more gravitational waves, it's going to cause the amplitude of this power spectrum at these really large line sizes to continue to increase. With our current data, we can put an upper bound on how much gravitational waves could have been produced. And you can see that in this yellow shaded region here. So everything inside the yellow shaded region is still allowed by our current data. So that would rule out things like those really dark lines at the top, which are above this yellow shaded region. But there's still a lot of lines that are in the yellow shaded region. Our data is actually still consistent with no gravitational waves too. So we have a lot of work to do here to get these error bars smaller so we can try to differentiate which of these lines actually represents our universe. So that's what a lot of people are trying to do, and I'll go through some of the people trying to do that. Not all, not a complete list, but some of the notable experiments. So, and the telescopes that I work on will have a little purple star on them. So in the past, we had things like WMAP, which was a telescope in space, Planck, which was a telescope in space. Oh, sorry, yes? Yeah?
There's a trend line for the correlation, so like it's increasing as the line size gets smaller, or?
Okay, so if I'm understanding your question correctly, you're asking if the correlation of these polarizations is increasing for smaller line sizes. Yes. Yes, it is.
And then it curves down, so it gets too small, it doesn't correlate as much.
Yeah, and it follows like similar shapes to, I'm sorry, I'm just gonna go back to here. So I guess so just like the temperature ones do that too, but specifically for our B-mode power spectrum. So I guess I didn't explain to you what's causing the rest of the shape. I only was telling you what's happening at the largest line sizes. So just like how we can have gravitational waves in the early universe, after the cosmic microwave background, we can still have gravitational waves. Like we have black holes that are merging, neutron stars, things like that. And that can cause our E-mode polarization, or the light particles that have that certain type of polarization, to actually get turned into this B-mode polarization. So it changes the polarization of this light. And that's what causes this part of our B-mode power spectrum. And that's why it kind of follows a similar-ish shape to the E-mode one. But the ones from the early universe are going to be down here at these largest line sizes. Yeah, so that's kind of why it looks like that. Okay. Okay, cool. So yeah, Polar Bear, which is a ground-based telescope in Chile. A BICEP 2, which was a ground-based telescope in the South Pole. They have other versions of this there now. We have the Atacama Cosmology Telescope, or ACT, which I have half in the past and half in the current. So this is one I work on, because we just took our final data this year, but we're still working on analysis, so it's still kind of going on. So that's why I have it half in both. We have the South Pole Telescope, which is in the South Pole, in CLASS, which is a telescope in Chile. And then going forward, we're going to have things like the Simons Observatory, which I work on, which we're hopefully going to get first light, so collect our first data mid-next year. LightBird, which is a telescope I work on that will be going to space, and hopefully will launch within the next 10 years. And the main goal of LightBird is to measure these really large line sizes for the B-mode and E-mode polarization to really get our error bars better. And then PICO, which is another future proposed telescope that would be going to space. Okay, so now that I've told you about how we would figure this out with our cosmic microwave background, I'll now go a bit into how we could directly detect these gravitational waves. But I'll do it in the reverse order. I'll start with the experiments first. So currently, the main way we try to detect these is using LIGO, which I mentioned earlier, or the Laser Interferometry Gravitational Wave Observatory. And it has two locations, one in Washington State and one in Louisiana. And it kind of just looks like this gigantic L. But it does this because if you remember that little animation of the gravitational wave going through the particles that's causing it to stretch and squeeze like this, perpendicular to each other. With this, it could measure, for example, one part being stretched while the other part's being squeezed. So that's why it's an L, or perpendicular. In the future, we're hoping to have LISA, which is the Laser Interferometry Space Antenna. So it's going to be a telescope going to space, which is pretty cool because we have 0 gravitational wave observatories in space right now. So this is the first one that will hopefully get there. And the way that it'll work is it will orbit the sun with the Earth. So in this animation on the bottom right, you can see the sun is the yellow dot in the middle, and this little blue dot is the Earth orbiting the sun, and you can see how the telescope will be orbiting along with the Earth. So I'll explain to you how these types of experiments work, but I'll explain it for LIGO, since it's a much simpler geometry of just an L. Okay, so the way LIGO works is it has these 2 arms, and they're really long. And it's going to emit this laser light that's going to come out of the emitter and go into this mirror, which is going to split it up. So you're going to have this light going down each of the arms of LIGO. It'll bounce off the ends and come back. Then when it gets back to where it got split, it's going to combine in such a way that actually causes all the light to cancel out. So you don't see anything in your detector, which is on the far right here. But as a gravitational wave goes through this, it causes the arms to stretch and squeeze opposite to each other because they're perpendicular or 90 degrees apart. And that causes these flashes to happen in the detector. So these flashes that they can detect are actually detecting gravitational waves, which is pretty cool. They can actually detect it's like a fraction, like the change in the arms being like a fraction the size of like a proton, which is some of like the smallest particles, which is pretty cool. Yeah, but you might be thinking, well, what if there was an earthquake and it caused all this weird flashing? Well, that's why they have two locations, one in Washington State and one in Louisiana. So they know they have to see the signal in both of the detectors to know it's a gravitational wave. Cool. So when we detect these, what does this actually look like, and how do we compare it to our theories or our predictions of the early universe? Well, we can put it on a plot that looks like this. There's a lot going on, so I'm going to go through it piece by piece. So on our x-axis, we have our energy, where the lower energy is on the far left and the higher energy is on the far right. Then we have our strength of our gravitational waves on the y-axis, where the weaker they are, the closer they are to the bottom, and the stronger they are, the closer they are from the top. So all of these lines here are simulations I did for different models of inflation, particularly when that skateboarder's in the ramp part of the potential. So I chose a bunch of different models and predicted using computer simulations what those gravitational waves would actually look like. You can then figure out what could these experiments like LIGO and LISA have measured or be sensitive to in the future. And you can put that here. So all this gray shaded region is where things like LIGO and LISA would be able to measure gravitational waves. You can also use astrophysical experiments. So our cosmic microwave background, galaxies, and element abundances, figure out how sensitive those would be to gravitational waves. And you can put them on the plot as well. And that's this peach shaded region here. But you might notice all of these signals that I simulated don't overlap anywhere with what these experiments could detect. And they need to overlap for these experiments to have, or in the future when they're built, to be able to measure these. And this motivates developing sensitivity in this regime. So for example, you can get better astrophysical observations, and that will cause this peach shaded region to get lower. But that's only going to let us know how much gravitational waves there could be. It's not going to give us any information of what energy they exist at because it's a flat line. So another thing that should be done is building these gravitational wave observatories to be sensitive to these energies that inflation, at the end of inflation when you have a skateboarder oscillating or going in its ramp. So yeah, they should probably build some there. There's been a little bit of work done, but more proof of concept. So hopefully that will happen in the future because it'll be extremely useful for us. Okay, so I know there was a lot going on, so I'll go to a takeaway now. So we measure our cosmic microwave background to be extremely uniform. And this is one of our main motivations for inflation. We also are pretty sure that inflation is going to cause gravitational waves to be emitted, which we are trying to measure using these polarization patterns in our cosmic microwave background, and directly using things like LIGO. And if we can detect these gravitational waves, it can help us peer into the earliest moments of our universe and understand how and why the universe actually looks the way that it does today. Thank you. I can take any questions. So yeah, if you raise your hands, I can call on you to get some questions. Oh, yes.
So that cosmic
Microwave background?
microwave background, that picture you took, is that as it is at any time, like now, for example, we will have the same picture?
Okay, yeah, I see. Okay, so yeah, I'll repeat the question, especially because this is getting recorded. Okay, so the question is, so I'm trying to get back to the photo, is does the cosmic microwave background look like, sorry, I'm so close. Maybe I shouldn't have said that, maybe I'm not. Okay, look like this at all times, or does it just look like that today? Okay, so it'll look similar at most times, but the temperature of these photons or light particles would have been a lot hotter because they're losing some of their temperature as they're coming towards us. But also, this will get slightly changed, which can also help us, measure things to do with astrophysics as well, so not the largest scales. So for example, when I was talking about, oh, of course it's not here. Okay, cool. So for example, when I was talking about how we have these E modes that can be gravitationally lensed or turned into B modes, that's from these photons coming from the cosmic microwave background, but traveling through the universe towards us. So it is getting changed, and it's causing some of these E modes to turn into B modes, so we detect them in a different polarization than we would expect. So there are things that do happen later in the universe that causes changes to this. So when we're trying to figure out what actually happened at these different times, first the scale really matters. So inflation is affecting these really large line sizes, which are so large that nothing astrophysical could cause these signals, these super large signals. Like something would have had to happen on like huge scales of the universe. Okay, it's a little bit sensitive to like when those first stars and galaxies start forming, but there's still a lot of work being done there. But in general, astrophysical stuff can't really cause things at this scale. So yeah, we have to model astrophysics and the cosmology at the same time to figure out, exactly how much it's changed and what could have caused that. Sorry. Cool.
We're looking at something that is like a really long time ago.
Color?
Talking about it created this thing and it's like a fingerprint that's there now because it's something that happened so long ago. And you're able to reference that from that. But it's
Yeah. Okay.
unravel a little bit.
Yeah, okay, so if I'm understanding the question, it's, okay, so we're measuring something from a long time ago, but it is getting a bit changed, so how can we tell the difference? Okay, so, one of the ways that we do this is a lot of people run simulations to figure out, what would these different things do and how would it change this? But also, for things that are more astrophysical, so things like the galaxy, stuff like that, we have a lot of other observations of that at different energies or different frequencies. So we know how those behave. So we already know what those signals can look like. So we know how it would present in this cosmic microwave background, things like that. I guess, yeah, so we know those things, so we know what those should look like, so we can take them out. But also, when we do this, we do it on a bit more of a sophisticated way than the way I explained here. But when we do these big codes to figure out what this looks like and what this means for theories, we include stuff from all of those all together. So we're modeling all of them at the same time to figure out how they would be changing things. And from our astrophysics alone, without what's happening at our cosmic microwave background in the early universe, it couldn't have looked like this without that. We couldn't have just produced that with our astrophysics. Yeah. Oh, yeah.
Is there any use to this in figuring out how the universe will continue to develop, or is this just understanding the past of the universe moving on?
Okay, so the question was, is there any use for this to figure out, how the universe would develop, or does it just help how the past and then why it looks like it does today? It definitely can help. So we still have a lot of questions on what happened at the earliest moments of our universe. So I don't know if anybody here has heard of, Newtonian gravity. So just the simple, we have our planets that are orbiting a sun and stuff. But then, Einstein came along and came up with his version of gravity. Well, those were completely different. They just worked on different energy scales. And if you go to things like a solar system, you can bring Einstein's gravity and bring it down to what we see on Earth. Well, just like that, inflation happened, and a lot of the early universe happened at such large energy scales that our theories can't fully explain it. So there's something missing, some higher energy version of Einstein's gravity that we're trying to figure out. And so, for example, if we can figure out what happened in inflation, it can give us an idea of which of those theories are correct, which will then help us have a more complete understanding of our universe, the particles that are in it, all that kind of stuff, which can then help us narrow down what could happen at late times. One example of things that people look at is something known as quintessence, which sounds kind of scary. But essentially, if you remember when I was talking about how the universe is starting to expand quite fast again, well, that's due to something known as dark energy. So it's causing our universe at later times to expand more rapid again. So some people look at quintessence because it's acting kind of like the inflaton. So what if they are the same particle? We don't fully know yet. So if the model of inflation that is correct could have caused dark energy too, that could help us figure out what's going to happen later. So yeah, I hope that answers your question. Okay, cool. Yeah?
Solving this expansion, I had some theory that was also a contraction on the other side.
Sorry?
I had some theories that there was a contraction on the other side.
Okay.
Same kind of thing going into the
Mhm.
Big Bang.
Yeah.
So can you say something about that?
Yeah.
Also, can you say something a little more philosophical about time? Is time only going forward or also back?
Okay, I'm going to start with the first question. Okay, so the question was asking about something known as the Big Bounce. So essentially, was the universe bigger before and contracting and now getting bigger again? So that is one of the theories of the early universe, but it's one that's getting fairly ruled out. So we can look at, for example, the way it changes our cosmic microwave background. In a lot of those models, it would cause these really large peaks in, do I have any picture of a power spectrum near me? It would cause really large peaks in this power spectrum at these large line sizes. So it would produce too many gravitational waves. You can rule it out from that. It also can cause this power spectrum to be tilted in different ways, which is getting more constrained. Also, it can affect the way that our large-scale structure, or like our cosmic web and all these galaxies and galaxy clusters look. There are still some models that are still allowed, but they're getting like more and more ruled out essentially by the day. So some are still allowed. They're just looking less favorable with our current data. But there are some experiments coming in the future that'll hopefully help make those error bars even smaller to have a better idea of, okay, are we going to detect one of these values, or are we just getting closer and closer to zero? And then the other one was time, about if we could only go, okay, so we personally, oh yeah, the question was, can time go backwards? So we cannot. Oh, this is going to go like real, okay. So all of the normal matter particles, which we're made out of, can only go forward in time. Light particles can go at the speed of light. There are theoretical particles that are completely theoretical. They're not proven by any means, for example, called tachyons, which the way that they interact with our like space and time is such that they could move around. But that's extremely theoretical and not proven yet at all. But yeah, so for all of our normal matter stuff, we can only go forward in time. Okay, cool. Were there any other questions? Oh, yeah.
I was a little bit confused by the skateboard analogy.
Okay.
And my understanding of that was that when inflation was really happening, it was happening more or less uniformly. But then as it slowed down in different stages, and so you get kind of wobbles in different by location. Is that correct?
Yeah. So when inflation's happening, it's happening fairly uniformly. We know there's an average temperature and like tiny changes, so there can be tiny differences in inflation that can also cause gravitational waves. But this is a time known as preheating or reheating, which is where this inflaton is creating all of our particles. This signal is very subdominant compared to the signal that we get during inflation. It's also at different energies, but it can cause some like pretty cool things to happen. At least I personally think it can cause some pretty cool things to happen. So for example, it can interact with itself and cause those like large pockets of like hot temperature in a room, or those large pockets of energy density. Those, like, for a super technical word, those are called oscillon formations. But it can cause these cool gravitational wave signals. But those would present at different energy scales and in different ways. So we could kind of tease them apart. But also, when we're trying to measure in our cosmic microwave background, how much gravitational waves were formed, we're only getting an idea on our power spectrum of how much gravitational waves there were. And we can also get a little bit more information by like how is this power spectrum tilted, things like that. But that's like a few parameters that we're projecting these huge theories down to. But by having another way to look for these gravitational waves, so for example, directly detecting them through like the skateboarder in the ramp, we could maybe disentangle some more theories. Like if the spectra look different, gravitational wave signals look different enough, we could maybe, okay, great, we detect a certain amount of gravitational waves, we've narrowed down our theories of inflation to a subset, but now we can maybe tease those together even more by detecting them directly and looking at how those look like. So in my opinion, they're like complementary methods and complementary signals. Cool. Oh, yeah?
How exactly does gravitational waves change the polarization of light?
Yeah. So the question was, how do gravitational waves change the polarization of light? Okay. It's a great question. Well, okay. So the polarization of light just has to do with how the electromagnetic fields are oriented. But as a gravitational wave is coming through it, it can cause almost like its motion to kind of change, and it can cause it to become slightly angled when it's doing that, which causes these small polarizations to occur. Yep.
Let's say hypothetically, if we detect the gravitational wave from the inflation, the LISA that you say that, and that will go into space, and that would it be able to detect it all around the, like cosmic microwave, we can see every place on the space, right? So similarly here, to detect that gravitational wave that affects the inflation, we'll be detecting all over, like if we're circling around the sun, but we'll be detecting all over
Yes.
the space.
Yeah, we'll be detecting all over space. And, oh, sorry,
That
yeah?
would be one of the qualifying things to say that the gravitational waves are from the inflation.
Oh, yeah, I'm sorry, I forgot to repeat the question. The question was, can something like LISA, as it's orbiting Earth, orbiting the sun, detect all of space, and can that help us figure out about inflation? Actually, exactly, yes, it does. And part of the reason is, we're going to have like black holes and stuff causing gravitational waves, but we're not going to see the same amount of black holes in every direction causing those waves. So the fact that inflation is going to be affecting everything around the same amount, we can try to tease those uniform signals away from all of these not uniform signals, so random black holes merging and things like that. So that's actually an extremely important point in why we can try to use this to detect the stuff from inflation. Cool. Okay, I think we can do one more question before we have to wrap up. Yes?
By what mechanism would this inflaton create all of the particles in our universe?
Great question. The question was by what mechanism could the inflaton, or the particle that causes inflation, create all these other particles? Okay, well, we know that different particles are coupled or like interact with different particles, right? So, for example, like we have light that can interact with different matter, things like that. And that has to do with if they're coupled in particle physics, if there's some sort of connection between them. We don't know what type of particle the inflaton was, but most of the models have it such that this inflaton is coupled to all of the particles that we see today. And if there's a coupling between these particles, when there's interactions, they can like turn into each other if there's enough energy provided. So just like how we can have, or like, you can think of like, if you think of like a nuclear reactor, and we have like different like atoms and particles and stuff and elements like being thrown together to make new ones. It's because they're like connected to each other. They can like interact with each other. So I guess it's kind of like that. It depends exactly what the inflaton is, but if it's coupled to these different particles, it can, when it's decaying or like going away, it can turn it into those other particles instead. And just like how we don't know exactly how it would be coupled or like talk to our regular particles, we don't fully know what I shouldn't say fully, we barely know, we only know the effects of dark matter, we don't know what dark matter is yet. And if it's coupled or like talks to the inflaton as well, it might also create those. So that's another thing that if we can figure out what happened in inflation, it could help us. Yeah, cool. So yeah, I think that's all the time we have for questions.
Thank you for the questions. I'll be providing some details on post-talk activities. First, I would like to thank all the volunteers. This is a purely volunteering event, so thank you to all those who volunteered with us. I would also like to thank our sponsors, these guys here. And make sure you fill out the feedback. We would really appreciate it if you do. It helps us improve our events. And after you fill it out, you can get a free sticker at the refreshment table. We will have activities in this building, the Independent Physical Laboratories on the rooftop, where you can get your hands on telescopes and demos and activities also on the lobby of this building. In addition, we will also have lab tours starting at 9:10. To go to those, you can go to the first floor elevator in this building at 9:05. There will be a volunteer there who will bring you to the labs. There will be 3 labs, one at 9:10, one at 9:30, and one at 9:50. Please come to the elevator at the first floor of this building 5 minutes before the time on your lab tour tickets. Please only come if you have tickets because there's limited space in the lab and we don't want any damaged equipment. We will also have 3D printed telescopes, demos, and refreshments. So check those out too, after the telescope or before, and with the lab tours. And finally, special thanks to Simran for today's talk. She gave her talk pretty much last minute and basically helped set this whole thing up. So thanks a lot, and have a good night, and hope you come next month.